All right, all of us that have calculators should have them out. Those of us that don't have it with us today, you better start bringing them tomorrow. Just a heads up. You can peek on someone next to you or behind you. That's what groups are for, is being like, hey, can I see? Because, yeah, wasn't quite prepared today. Okay, you guys are playing with the second x to the -1 button. Remember, if someone doesn't have a calculator, also show them how you got there. That's going to be helpful. You guys figured out, I mean, you're resourceful, right? Edit means, okay, let's change something. When we go on in, this one's square. If you just see a 2 by 2, you won't know what's what. But if I were to go to my other one, which I think was a 3 by 2, is that right? Guys, check out 3 by 2. Do you see this m by n thing going on at the bottom? It's called order in your notes. This is exactly what's going on with the 3 by 2. So my question to you is, what does m stand for and what does n stand for? What does the 3 represent? 3 rows. And what does the 2 represent? Exactly. So over here in our notes, I need us to go ahead and fill this in because it's something we're going to have to kind of remember. Not memorizing. No, it could be like a question on a test. What order is a certain matrix? But m is going to be how many rows. N is going to be how many columns. And A sub mn is notation for the entry in the mth row, nth column. In the mth row, nth column. Who's played Battleship before? That's it? Oh, okay. Oh, it's depressing. Anyway, Battleship. The point is, you cannot see the ships that your opponent has put on their board, where they've put it, right? For those of you that have played before. You can't see it, so it's hidden. You have your ships, and you put them in different places on a grid. You put ships down, and then your opponent ships down. You have to say something like B, how high does it go? B5, I'll just be safe. B5. And so there's like, B's are they the rows? And then 10 is the columns. I haven't played them forever, you can tell. Okay, the letters go down, the numbers go across. Okay, so if you say B, then they have to go to the B row, and then 10, they go over to the 10th or 5th, whatever one I said. And they have to say, haha, is my ship there, or if it's not there? If it's not there, they say, miss, because you're like kind of throwing bombs when you say the different. They're like, miss, you didn't get my ship, and then hit, then you're like, aha, and then you have to put down, okay, but then there's different sizes ships, like 2s and 3s and 5s, and is there an 8 one? Anyway. And you have to like hit them so many times to like sink it. Anyway. But you can think of a grid. That's what a matrix is too. So if we're talking about A sub mn, we're talking about the mth row and the nth column. So for instance, if I was to ask you what entry is in this matrix, what would you fill in for A sub 3, 2? Not 32. I know it looks like 32, but it's not. And there's not going to be a comma or a dash or anything else. Just A32. What entry is in that spot? Do you guys agree with Lainey, 1.45? Check it. Mth row, nth column. So if I say 32, I don't mean 32. There's not even 32 anythings in there, right? But that just means the 3rd row, 2nd column. Now, I know you're like, I like Battleship better because B10, and that's why they didn't do battleships with matrix notation. So if you said 3, 2, they're like 32, or 1, 5, is that 15? Anyway, it just gets too confusing. But in matrices, since we're keeping everything based on numbers, then 3, 2 just means 3rd column, 2nd row. So that would be 1.45. What if I was to ask you to name 3.65? How would you name it? What would the notation be for that guy? A, 2. Does that make sense? 2nd row, 1st column. So you can either be given an actual entry and you go find it, or you're given, given notation, you go find the entry, or you're given an entry and you write the notation. Good. So M by N means row first and then column. Row first and then column. Here's the dealio, kiddos. Have we done subtraction? What? That's not the right word. Psh. What came before elimination and how we solve systems? Lo siento, I apologize. Oh, hey, you're a genius. That's exactly what I wanted. I put the totally wrong word whatever year I wrote that. That's weird. Not subtraction. I mean, subtraction is elimination, isn't it? Like subtraction, addition. I apologize. Okay. Solving systems. Substitution. It's good. Elimination. It's great. Row echelon. It's hard, but it's for harder problems. What can you say, right? It's hard, but it's for harder problems. Matrices. Ooh. Okay. Matrices. We're going to see a little bit more. Remember with row echelon form how I was talking about the stair-step method and how I was talking about a systematic approach? And I want you guys to kind of be thinking like programmers a little bit, to not just say, hey, one problem, one solution, let's figure it out, but instead a whole category of problems and maybe a solution or a way of solving a whole category of problems. Programming technology to do it for you. We're going to kind of continue on that thought or in that thread of thinking with Chapter 8 with matrices, because really technology is a big, or specifically your calculator, is going to be really helpful with matrices. But once again, your test has a by hand portion as well, because you have to kind of understand what you're working with. So you're going to have to be able to do some things by hand also. So matrices, you guys can see them in your calculator. We've talked about the order, so I want you guys to take a second with these 4 different examples, and I want you to give me the order, the m by n for each. What would you have to type in to your calculator in this part right here, m by n, in order to make the right size to put in your matrix? Ready, set, and you, yourself, and you. Let's see if we can get them all right, or at least the majority of them. Worst comes to worst, you can always test it in your calculator after and be like, oh, do I have the right ones? But the number of rows first, then the number of columns. P.S. A and C should be pretty easy. If you guys are wondering what's going on in the back of my room with random candy on my desk, Senior Brache is like, hey, candy, sell it for missions. And I'm like, all right. So, anyway, if you want candy and you're not allergic to peanuts or peanut butter or chocolate, good point. Very good point. Or artificial coloring. Or why did I say A and C are super easy? What's A's order? It's just a 1 by 1. How about C's order? Doesn't matter if you had it right or wrong, right? Sweet, that's easy. All right, how about letter B though? Good, 1 row, 4 columns, yeah? If you're making a spreadsheet, you'd have to, okay. How about D? Got it. Okay, getting the hang of the order, just the size? Okay. There is a whole college class kind of built around matrices called linear algebra. It's kind of interesting. If you guys know any people going to college in any sort of STEM field, you can ask if they've ever had to take linear algebra. Computer programmers do, engineers do, any like actual math majors, whatever those look like. There's applied and pure and other things they do. Who else did I hear recently had to? I think like econ majors. I think they have to take linear algebra. Anyway, so remember pre-calculus, pre-everything, future math, so we're just introducing the idea of matrices. They could be used in all sorts of different ways. But we're only going to use them for systems of equations and then learn some fundamental stuff about them. You guys just named one that was a 1 by 4 and it only had 1 row. So maybe it makes sense that we could actually call any 1 by n a 1 by 2, a 1 by 3, a 1 by 10, a 1 by 20. It's just a row matrix. There's only 1 row. Similarly, a column matrix would be an m by 1, meaning whether you had an A11, an A12. Actually, I won't stop it. An A13. Whatever size you have, A1n, whatever size you have, it's still just 1 row. If you have a matrix where A11, first row, first column, A21, second row, first, A31, no matter how many entries you have, you still have 1 column for a column matrix. And then for a square matrix, You guys have already seen them. See what I'm talking about? I'm just showing you notation. A11, A12, A3, A21, A31. We could just keep going. We could just keep going. We could just keep going. But the long story short is at the end of the day, you're going to end up with finishing your matrix at an A. There's no reason to have an N and an M because they'll be the exact same thing. If you want to think about it this way, I could put an A22 and an A33. And it's just going to keep on continuing, keep on continuing, keep on continuing. You're just going to end up at an AMM. So if it's like a 5 by 5, you'll end up at an A sub 5, 5. If it's a 8 by 8, you'll end up at an A sub 8, 8, etc., etc. This last one is a special type. And these ones so far don't really care about what's inside. It's just talking about the size. But this one cares about what's inside, what the actual numbers are. And as I write that, AJ, go ahead and ask your question, kiddo. Well, it could be n by n. Like we could put the n, but the deal is it's always going to be a square matrix is always going to have the same. So like a rectangle has a length and a width, and a square just has a side and a side. We could say the square has a length and width. It's just the same thing, so we just call it side. And this one, instead of making like a third letter, we just say, well, M rows and, oh, by the way, same number columns. Does that kind of make sense? An identity matrix says there is a leading diagonal that's going from the top first entry all the way down to the bottom last entry. A leading diagonal of ones, and then there are zeros everywhere else. Now, technically, this little description of what it looks like does not tell you what it does. It doesn't tell you how it's an identity matrix. We've talked about how the number 0 is an additive identity for normal numbers because any number plus 0 is itself. 3 plus 0 is 3, pi plus 0 is pi, e plus 0 is e. 0 is the additive identity of normal numbers. What's the multiplicative identity of numbers? If I want a number to stay the same with adding, I just add 0. If I want a number to stay the same when multiplying, yeah. So 1's the multiplicative identity. So far all we know is that this matrix is an identity. Which one? Well, we'll have to figure that out. But it is an identity. It is pretty important, but don't worry. We'll talk more about him as we come. But he's always a square matrix, first of all. This one's a 4 by 4. He's always a square matrix, number 1. And number 2, he always has a leading diagonal of 1s and 0s everywhere else. Yeah. No, not specifically. Not that we can't program matrices into computers, but no, the 0s and 1s don't have to do with binary. Good question, though. You'll see why the 0s and the 1s are where they are, but it doesn't have to do with the whole coding true-false idea, which is what binary is built on. Oh, sorry, guys. I thought I made that bigger, and it didn't really work, did it? There we go. Okay. Section 8.1 says matrices can be used to solve systems. And kind of like the thumb trick for partial fractions, would you rather me with something new start off with a crazy hard problem or with an easy problem? Usually most people would say an easy problem, right? So we're going to start off with the easiest type. He's alive. Talk to me real quick after about this. We're going to start with an easy problem, and I know it's easy. I know you could solve this with substitution. I know you could, although who wants to solve that with substitution? Anyway, I know you could solve it with elimination. What would you guys multiply, the top or the bottom, and by what number to eliminate? Yeah, I would totally multiply the bottom by 2, because then the y's would cancel, right? Okay. So I'm not saying that you couldn't do elimination or substitution, but the easiest type of problem that I can show this on is one you already know how to do another way. But it's the easiest type of problem. Remember, This is kind of some of the programming that can train or show a computer how to solve a system. Matrices are a great way, and it's actually even a little bit better than row echelon form, but it still kind of uses row echelon form. But it simplifies the coding in that when you go to solve, you're going to actually take this word problem, not this word problem, but the system of equations, 8x minus 4y equals 7 and 5x plus 2y equals 1. You're going to take the system of equations and you are going to transfer this into a matrix. Taking each of the elements from, as long as everything is lined up as far as the x terms are first, the y terms are second, and the constants are last, you're going to keep them in that order. If they weren't in that order, you would need to rearrange them in that order. So first of all, some of you guys are realizing matrices can't be used for those crazy ones that we saw with x squareds or with e's, like e to the power of x's. It couldn't be used for that. It can only be used for linear equations. However, we would take each of the entries, which this is a 2-equation system, 2 unknowns, x and y, 2 equations. Okay, so we should be able to solve it. But our matrix ends up being what size, guys? You already forgot. It's okay. How many rows? How many columns? So 2 by 3. So you need to put in a 2 by 3. We already saw how our calculator can do row echelon form, right? But let me show you how row echelon form works with the matrix itself. Because last chapter, we were still working with the x's and y's in it. But with the programming, it's going to be a lot easier to get the x's and y's out. So here's a matrix. All the x's and y's are gone, but the meaning still remains. X column, y column, constant column. Equation 1, equation 2. So the rows are the equations, the columns are the different types of terms. Okay. The idea of doing row echelon form in matrices is to work by columns. We're trying to get each column to be what we need it to be. Now, if we're just doing row echelon form, that's the one where we use back substitution in order to solve. We would say, okay, hold on. Wait a minute. For row echelon form, let's remember the stair step. Didn't we want to get a system of equations where we had 1x plus lots of stuff, and then 1y plus lots of stuff, and then if we had a third equation, 1z with equals, right? That was the stair-step system. That's how we wanted row echelon form, with 1 and 1 and 1. Oh, 1 and 1 and 1. What does that kind of sound like? The identity matrix. Interesting. And then, if you guys check it, if we were to think about this as a matrix, 1, 1, 1. What's underneath these guys? Zeros. So how do we get our matrix to look like this? Because we liked row echelon form because it was super easy. If you knew this, plug it in and get that. If you knew both of them, plug them in and get that. We need ones and we need zeros. But on the board, I say work by columns. And so we're going to get the 1 first, then we're going to get the zeros. Then we're going to move on to the second column and get the 1 first, then get the 0. Then move on to the third column and get the 1. If you do it in another order, you might mess up all the work that you did in getting the 1. Or vice versa. If you get the zeros and then go get the 1, you might mess up all the 0 work that you did. So let me show you how it works for a little baby one. If I need the 8 to become a 1. Wait, we did this when we were doing equations. If we needed the 8 to become a 1, what would we do to everybody? Divide by 8. Okay, so I'm going to go ahead and I'm going to show some notation as to what I'm doing. These are actually called row operations. I'm going to go ahead and say, you know what, this first row is great and all, but I need everything to be multiplied by 1/8. It's possible in these row operations to actually like switch the equations or switch the orders or do an operation and move it to another row, etc. So I'm saying what I'm doing. I'm multiplying all of row 1, every single piece, by 1/8, and I'm putting the answer in row 1. So that way if I was to try to program that, I'm telling the calculator what to do, or the computer what to do, and where to put the result. So kiddos, if I was to do that to the whole first row, what do you get for the first one? 1. How about for the second one? -4/8. -1/2. How about for the third one? 7/8. Now, When we're working by columns, the first thing we get is the 1. We don't even worry about the other equation, so I'm just going to rewrite him. 5, 2, and 1. Technically, we're going to learn that this is called a doubly augmented matrix. So we put this little dotted line so that we can see these are the variables and these are the non-variables, but either way. Now, is the 1 there? Yes. Okay. Once the 1 is done, what did I say you're allowed to move on to? Okay, the zeros. Kiddos, if I wanted to get a 0, right? If I wanted to get a 0, what would I do? With elimination, like the old school, we would do the little caret with row echelon form and take it over. If I wanted to get rid of x's, what would I have to do? Make them match, but opposite, right? But look what we just did. By multiplying by 1/8, is it as hard as having to make these 240 now that I have these two instead? It just got a lot easier. By having the 1, can't I say, oh, hey, what if I just multiply this by -5? Oh, -5, row 1, plus row 2. This step of multiplying by a coefficient was and will be always the way to get the 1. Multiplying an entire row, or I should say multiplying by the reciprocal or dividing by the coefficient that's there, that's in the spot that I need a 1 in, that's always going to be how we get the 1. And multiplying by the opposite, multiplying the row with the 1 that you just made, multiplying it by the opposite will always be the one to get a 0. And here's the cool thing. I just use the words always, meaning whatever possible system that you would give a computer, you can always get the first to be a 1 by dividing. You can always get the rest of them to be zeros by doing this little multiply by the opposite and add. And that's something you could program a computer that can go way faster than you. Steps to follow, except they can't just stop at the first column. Now hold on, let's see how this works. What happens when we multiply the top row by -5 and add? Okay, we have to do it term by term. Ready? First column, first row, multiply by -5. -5 plus 5 is 0. Oh wait, hold on, we're only changing the second row, right? So keep the whole first row. Keep the whole first row. He's fine. He has the 1. We're only working with the first column. And the first row is fine. He has the 1. Second row is what we're trying to change. So -5 plus 5, 0. Ooh, what's -5 times -1/2? 5 halves. 5 halves is 2.5, right? What's 2.5 plus 2? 4.5, or some of you might have done the fraction way, 9 halves. 5 halves plus 4 halves, if you got common denominators, 9 halves. 4.5 or 9 halves, either way. Just a warning. Fractions will be easier to do mental math with. Decimals are going to get hard right about the next section, or the next step. Ooh, what's -5 times 7/8? Now, some of you are like, this is way too much math to hold in my head. Couldn't you do a quick little over here to the side? And couldn't you do, okay, wait a minute, so I'm going to have -5, I'm going to have 5 halves, and I'm going to have 35/8. And what are you trying to add them to? Couldn't you show the math? 2 is going to be 4/2, which will help. I could change that. What could I change 1 to make it easier to add? 8/8. Good. So if the mental math is too hard, you can always actually set it up. Then you end up with 0. You end up with 9 halves. And then you end up with 35 plus 8. That's going to be 43/8, right? Ooh, where was the negative? Nice, good catch. Where was my mistake in my mental math? The negative needs to be right there. Good. So then if I do -35/8 plus 8/8, then I will get that -27/8. Because 9/2 came from this one, -27/8 came from that. Is my first column done? Do I have a 1? Yep. That's for the 1x. Do I have a 0 underneath? Perfect. And technically, guys, I should probably erase this. We're not doing this one because there's no z in this one. We're doing more like a little baby one where we get the y equals. There we go. We're doing one like this. So what's it time for now? I've done the first column, and now let's go ahead and move on. Second column, what's the first thing I have to start with? Do you remember which one comes first? The 1. Okay, how do I get a 1? I divide or multiply by the reciprocal. So what do I do to get the 1? Multiply by 2/9. I'm going to do 2/9 row 2 into row 2. I'm only dealing with row 2 because row 1 is fine. I'm not allowed to start with him anyway. I need to get the 1 before I get any zeros. The reason this order works is because, guys, what's 2/9 times 0 going to be? 0. Perfect. I don't mess that up. I need that. What's 2/9 times 9/2? Perfect. What's 2/9 times negative 27/8? If you don't like it, write it off to the side. But it's not that bad, is it? 2/8 reduces, like Lainey was saying, there's a 4th in the bottom. And then what does 9 and negative 27 reduce to be? -3. So -3/4. Now, it's not an identity matrix yet. Row echelon form just had us getting 1s and then 0s. And then there are all sorts of messy things up here. So we got the 1s, we got the 0s, we're done with row echelon form. Leo? Oh, because to get a 1, we always need to divide by the number that's there. Or another way of thinking about dividing is multiplying by the reciprocal. So we divided by 9/2. It's a lot easier mathematically to say times 2/9 instead. Because remember, the first column's good. I moved on to the second column, and I said, wait, second column. Technically, if I take this away so that you guys can see the size of the one we're dealing with. We got that. Second column. We need a 1. So I was looking here, not there. Does that kind of make sense? Okay. Guys, this is in row echelon form. It's official. Why is it in row echelon form? Because if I were to rewrite this as a system, I would have 1x minus 1/2 y equals 7/8. And I'd have 1y equals -3/4. Is this row echelon with the stair step? Do I have one and I'm ready to plug in to find the other? And some of you are already doing that. Row echelon form is easier because you don't have to get the full identity matrix. You only have to get the main diagonal and zeros below. You don't have to deal with the above. But the dilemma is you're not done at the end. You're only part way there. You know one answer, but you still have to plug in to find the other. So x minus 1/2 times -3/4 equals 7/8. You guys already got that to be plus 3/8, right? Oh, hey, what's 7/8 take away 3/8? 4/8 is just 1/2. So at the end of the day, we end up with the point 1/2 -3/4. Now, if we had done our little substitution, that would have been gross. Elimination, that's right, that would have been easier. Elimination step, we would have multiplied this guy by 2. That would have canceled. That would have been 10. 8 minus 10 would be negative. 8 plus 10 would be 18. 7 plus 2 would be 9. 9 divided by 18 would be 1/2. Check. Did I say this was the easiest way to solve this guy? No. But I said this method is easiest on an easier problem. So I'm showing it to you on the easiest problem. But here's the dealio. Row echelon form is good in that it gets you to something where you could just take and plug in and solve. It's good in that it's a system that will work every single time and you don't have to see the problem and reevaluate substitution or elimination. Which term do I want to do and how do I make it match? It's easier for programming as well. But dilemma, row echelon form again. You're not done at the end. What did we still have to do down here, guys? We still have to do some substitution and some plugging back in. Whoa, I left this whole page for us to work on and we didn't need it. Go team. But there is something cool called RREF. Not just REF. What we just talked about was row echelon form, but there is something called reduced row echelon form. I'm going to actually move this before the other page, before the example practicing it. We don't have to stop with just the ones and then the zeros below. We can actually keep going. Reduced row echelon form says, get all the way to what we now know is called the identity matrix. Keep simplifying until you get all the way to the identity matrix. Meaning, don't just stop with the ones and the zeros below. Get the ones and the zeros above. Don't just stop with the ones and zeros below. Get zeros above also. Real quick, just tap anybody in your group who's falling asleep. There's like 3 of you. Or 3 groups that need to help them out. Okay, it's called Gauss-Jordan elimination. It's called reduced row echelon form. In your calculator, it would be called RREF. We'll play with this more tomorrow, but here's the idea, kiddos. If we were able to get this guy all the way down to, and I'll show you at the very, very bottom, all the way down to having ones in the leading diagonal, zeros everywhere else, following the system that we talked about in that easier example. If we were able to get all the way to the identity matrix, ones all the way down, zeros everywhere else, guess what we would get over here? What column is this? Which variable? 1x is going to equal, okay. If we do the second column, what's that guy going to be? 1y equals, and if we do the third column, 1 equals, you won't just have 1, you'll have it all. Dun, 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 dun. Wait, but you're like, I can do a 3 by 3. Okay, fine. How about a 4 by 4? How about a 5 by 5? How about a 10 by 10? Our system of like, take the 2, take the 2, take the 2, take the, that's going to get way worse as soon as you get to 4, or as soon as you get to 5, or as soon as you get to 6. This matrix method says, give me anything. I'll get here, and I'll get you all the answers that you want. Pretty cool. But tomorrow we're going to have to work on it together. Now, hold on. Do you guys see how many numbers there are? Do you see what I was doing over here with this easier example? Oops, back one more. How much mental math was going on? A lot. And then I started kind of writing out the mental math. Tomorrow at the very beginning of class, I think we're going to have to practice our mental math just a little bit. So that will be a little bit sharper for what's to come. Okay, we're going to have to practice our mental math just a little bit to be a little sharper for what's to come. You guys can go ahead and pack up. Don't move, though. Don't get up. To that end, oh, I only have one Valentine left. They're missing. Oh, I was going to help us do mental math today, but I don't think I can. Oh, sorry guys, my mental math cards are missing. I don't know where they are. Someone must have been having too much fun with them. All right, be ready tomorrow. That mental math, we're going to have to work on it. You guys can start this homework, but probably not finish it. Just kidding. Definitely not finish it tonight. Bye, guys. Yeah, just put it in the can.